Alright. It's time. It's late, but it's time. It's actually a lot later than I would like it to be. It's probably extension with due dates. And I let myself relax a bit and go a little more in depth to get that deeper comprehension I really wanted. I still don't like being up this late and working on a valve. That was a failure on my part, but it's okay. I accept that. Anyways, let's get some more of this. So very familiar with this problem. We just talked about it. Now I have actual numbers, so our permittivity or the alpha is 1. We're given the initial conditions. So the entire bar, except that left end is at 20C, the left end is at 50. This bar's at 50 meters long. We have some parameters here, so our delta x is 1 meter, delta t is 1 second. And got the general plans what we want to do. I want to make a plot of it. It's a very pretty plot. It's very fancy. And there we go. So, sort of basics first. We should probably import numpy. If you don't import numpy, well, you just don't know what you're doing. You're failing, you know? You're just not doing it right. Let's go our basic constants that way. So our delta x is equal to 1 meter. I should put a comma here. 1 meter. Oops. And 1 delta t is equal to 1 second. The actual total speeds aren't really too important, so we just need to know is the number of each. So we know our number of discrete x units is 50. So we have 50 meters, and 50 meters divided into 1 meter chunks is 50. As for our time, we're plotting this for a total of, I believe it's 5 hours. Let me double check. I think it's 5 minutes when I'm plot a line for 1 hour. Let me double check this. Oh god, I just read this and can't seem to read. There you go. It'll be 5 minutes for 1 hour. And so our number of time steps going to be 360. If I'm really confused about it, I can double check because, well, sometimes I'm not right with my unit conversions. So, sanity check. It's 6,300, so that's all good. So now remember, we're going to use a essentially matrix. Matrices, I always want to say matrices, but it's a matrix to solve this problem. Will not be represented the way we had it before. That's all the zeros. So actually going to create a condensed version. So remember, we have 3 different matrices. One of all be different coefficients for j plus 1 terms or next time terms. One that holds all of our next time terms. One that holds all of our known current time terms. So what I'm going to try to do is say, alright, we have one for the known values. That's going to be an array. We're going to have one for current temperature. Previous iterations, I have called this current temperature. I found that gets very unruly very quickly, so I usually take it down to T. It's a much easier way of doing this, trust me. We can actually see the codes on the screen instead of it scrolling way past, so that's really what you want. And we're going to say next time coefficients for big matrix. Very short order. It's going to be represented no difference, but we'll get that. So, we're on values. We think for now our t, obviously that represents our bar, so our actual physical represents our each points in our bar, so each delta t is going to be one temperature point, so I'm going to represent this with a full, so initial conditions, or it's at 20C, so 20.0, because of our very left end, where it's 50.0. There we go. That's pretty easy. Get back to known values, so I'm now going for next time coefficients. As you remember, we had those 3 essentially diagonal rows, the 1 plus 2r and the 2 minus r is surrounding it. So the way this works is actually a true 2-dimensional matrix. Number 8, but only going to have 3 of these. So what we're going to do is take all those diagonals, so we're running across this way, quote unquote rotate them to horizontal and represent them that way and just top off aim for x as 0. So what to do, so I'm trying to think about way to do this. So np.full to represents for the entire length of the bar, more or less. And x should be the length, and if I'm confused by that, I always put the numpy help. Numpy full. Well, first argument should be the length. Double check, because you know, not perfect. Full shape fill value. So we can say the shape. What I really want is probably a tuple 3. So one 3 rows, and want the length to be n sub x, because that's how many terms we have. And so we'll make each of these. Oh, bother. We have to reset them anyways, essentially. So just make them 0 and we'll set them as is. So time coefficients. That reminds me, you don't actually have R defined yet. So let's do that. So now for this 1. So R. Let me put my notes. There we go. R is equal to R delta t times or alpha divided by 2 times or delta x squared. So delta x squared. Let me put some parentheses here that gets parsed correctly. There we go. Always defines. Good stuff. Great. So since we're going to rotate this diagonal to horizontal strips, we'll say, hey, this full line is going to be negative r. Copy paste bits. Oops, come here, friends. The next one, the middle one, is going to be r 1 plus 2r. And our last one is going to be negative r again. Using a step like this, that's because how SciPy solver, which we're using, takes in these sort of equations. They use a essentially optimized method of solving a solution of equations with a patterns matrix, which we have. It's all in diagonals. So this will be more later, a little later on. Alright, so this is done. Core NP is done. Unknown values. Alright, my apologies. Need to check something real quick, and all good now. So, alright, back to what we're doing. So, this main one right here, say alright, the bulk of these is going to be equal to our basic equation before, basic model we had. So, I can't show you the paper on the screen, sadly. I'm going to go back to previous video. Such a shame. We said, for each of our known values, where, alright, J is not plus or minus anything, it's the current time. We said it was equal to the time. I'm just going to kind of bodge this. I'm not going to use proper notation just yet. I know it's been very scary, very bad. So it will be r times t minus 1 minus 2r minus 1 times our current t. Let me keep a great representation for now. No, it seems kind of weird and useless, but we're going to convert these t's into something that makes more sense. And that should be a minus again. Oops, hi friends. Let me double check that. It's t. Yeah, alright, we're all good. Sorry, I do have my notes beside me because I'm trying my best to commit this to memory, but unfortunately I've not yet. Alright, so here we are. So a basic equation for the right half. Half that we know all our values for. So, what I'm going to do is convert these into usable values. So, instead of t minus 1 with some arbitrary points on here, well, we're going from here to here, one on bounds. Well, if it's not bounds, we just shift back one if I is minus 1. So we'll do just that. We'll say, alright, we'll store at this bounds and go to negative 2, so go back 1. This one, oops, I need you there. Let's say this one, we'll just keep the same because there's no additional subtraction. this one, since it is I plus 1, we'll shift to a right 1. So it would be 2 to ends. And he adds in very, very important multiplication symbols. So there we go. That takes care of like 99% of all the stuff I need to worry about. Not bad, right? Not bad. So, boundaries. Now the very left boundary, there's a constant temperature, it doesn't change. We're not going to try to modify that temperature at the beginning at all. So we can say known values. The very short or left boundary. Oops. Oh no. It's parentheses instead of brackets. These brackets, abrasive recruiting ones. So no, the temperature does not change. We should just say is R times RT0. Easy peasy. That's it. Doesn't change. It's just that. Multiply times R, all goods. But what about our insulated boundary? Well, since insulated, it has no heat flow, so it must be equal to the flow previous, the temperature previous to it. So you can say T minus 1, or T the very rightmost, is equal to T and negative 2 over 1 just to the left of it. So force that to be true. So it calculates values in addition. So we kind of modifies, we're going to say plus equals. Real quick. Just to make sure we don't actually use any of the stuff we've done in here, because this applies to everything. This is spec stuff we need to take account for our edge cases. Quite literally. So we have plus equals to don't actually overwrite any of this great stuff we did up here. So R times T neg 1. Oops. Here we go. Not bad. So this will iterate and hopefully calculates all values as we go forwards and how that temperature changes. I'm still plot these. So it's every 5 minutes and 5 minutes and seconds. I believe it's 300s. Again, I should double check, because never trust yourself to do mental math, because you make mistakes. That's minute meters. There you go. Yeah, it's 300s. Ha. So if I'm on 300, so if the current time in seconds evenly divides into 300s, yes, we're putting over seconds. Oh, we do actually access PT. So this is already kind of iterating as we go into the size of the bar. That's probably steady of me. That's okay. It happens. Anyways, so this is a clean divisor of 300s, i.e. it's 5 minutes. We should add or scatter plot, so add scatter. Once this works, and this does work without too much debugging, get to run, I'll go add those labels, make it easier to read, because I appreciate those things. Alright, spats, I believe, good to go. Let's check this out. Oops, wait, forgot, what's more bits? Got known values. We don't actually solve for it anywhere, do we? So we're going to use that special banded solver. So let's go for documentation of that. So sorry about solve bandeds. Check packages. I think it's an alg. Here it is. Just a basic one. That's fine. From scipy dot in alg. Algal. Port solve bandits. Let's go get our new temperatures by solving this matrix. Well, system of matrices, I've not taken an algebra, I really need to. It's quite sad. Solve bandits. So I have calculation how this works, but I check documentation anyways, because I'm that kind of person. Parameters. So take a look at this. INU takes a tuple V, so it's how many diagonals below a middle and how many diagonals above a middle we have. So we have one of each. 1, 1. Iron range 0. Oh. I'll fix that up as well. Alright, so these self-bandeds. Got our lower upper bounds, that's pretty easy. And we need to get our two matrices. This one I'm not as clear on, so I have next time, yeah. Next time efficient. And then or of one or known values. Take a look at that. That looks legitimate. Check everything else. Looks legitimate. Ooh, except for this. Since these are one off from our diagonal middle, they can't actually be the exact same length. Because it's a square matrix. To go down, it's on diagonal. It can't just be one short of each one. So let me go correct that. So maybe this one. This is the upper bound. It should be chopped off at 1. If this isn't quite right, we'll fix it. Because it will look very, very wrong. This means I made a mistake. I do those often. Look, syntax around syntax. Take a run. Need a evaluation equals, not assignment equals. 0 is missing shape. At line 10. Oh, oops. X. Let's take a look. Ha. Solve painted. Oh. Ha. There we go. Looking at ands. Must not include instant ands. So, wasn't quite right. We'll change it real quick. So instead of this, it's this. This, it's this. So I fixed it. Probably won't. Yeah, I did. That's right. So I'm going to bug this for bits. I've done this before. I've had this exact same issue before, but trying to do visually debug this is going to be a hassle. So I'll be back. I'll explain what I did wrong. I'll explain why it's wrong. Just in a sec. Ha! Found it. So you're foolish. It should be -1 because when you got was nans, and we're kind of breaking the entire array by adding a single value to the whole array, and everything breaks. So show this again. Open account double scalars. And it's camping on small. Just fix that. Oh, that's okay. We have some more dimension issues in here as well. Since we're actually modifying the internal ones but not boundaries, we really need to make this one to -1. So I hope I won't fix that problem just yet, but that's okay. Time coefficients, yeah, we actually need this to be nx -1 because we need to ignore those boundaries, and these will hopefully help deal with the issues of being a smaller. Look, shapes seem to be not compatible. So, with shapes on, that's okay. Values nx -2. Shape array to shape 46. Try -1. Some of this is just making sure you guys are correct. 847. Alright. Well, it happens. Sometimes all I gotta do is take a look at it and make sure you're doing it wrong. So this should be okay. So extend our boundaries for our coefficients, since those obviously weren't quite right. It's going to only the internals. So our 1's -1 should be a-okay. And for our x0's a range, that should be fine. That's just plotting, don't even worry about it. Equals np.full, which will include our two boundaries. And so that's why we have to do this and this. That's easy. Actually, probably easier to do is check out next time coefficients known values. Next. There we go. This is Python, it's like len, isn't it? Free. Okay. Oh, what size? No? Alright. Well, we can do this instead. 48. There we go. And the length of our amazing known values. 50. Yeah, that'll come with a damper, wouldn't it? because they're not the same dimensions. So let's go on values. So if it's nx minus 2, of course that will give us an error right here. Cannot spawn present parameter 48 to shape 46. So take a look. Times t minus 2. 46. Hold on. 48. 48. Length of t. Oh, right. I see. Because now we're subtracting one off both those ends, and that creates an issue. So instead of having it make me smaller, I really want these bigger, don't I? I do. See, part of this debugging process is learning. I'm trying to make good judgments for, I want to say, to debugging or learning. So I think I know this will be a good time. I'll make that change real quick. If it doesn't work, I'll cut you off. I'll get back to it. Anyways, let's make this an x. Coefficients. Yeah. Alright. 0 is 48. Done values. Length of t. Fine, it's caught one. Alright, this is just stupid. I'm going to just do this. This 4% apply to all of these. I should be able to just do this straight and not worry about cutting off ends, because we do have ends in here and do have extra data. So let's try that again. Okay. Oh, it needs to be inside. Respect to indents. Oh, there we go. Well, that's not most helpful thing I've ever seen. That's still not most helpful thing I've ever seen. And scatter. Y equals t. I want to do it every time then. Might just make a new label for each of these and go give it documentation. Yeah, that's not quite right, is it? Let's make sure. Print I. Yeah, it goes over time, so we're fine. Zoop. Zoop. Equals t. So random 1 next time coefficients my values. Yeah, I'm bother. Alright. Let's go with staples. That'll probably help us a bit. Besides, we'll do this anyways. Sum.full. Here you go, graph objects, add scatter. Oh god, it's not parameters. Believe it's a name or label. So let's take a look at both. See if we find any name or label. Got name. Try that one. Name. Cool, just make this a format string. So F quotes I make this still better. We'd prefer to say, oh yeah, it's time at X minutes, but this one needs help. And put this on reduce name equals initial. Initial. Go. Oh. Right. That'll make a difference, wouldn't it? That's going to really chug since that's doing all of them. That's okay. Let me chug for bits. Let Firefox chug for bits. Come on, bud. That's okay. Or maybe it's not okay. Oh boy. Jupiter's having a good time. I have to stop recording. Oh, okay. We'll give us the answer. That's not what it's supposed to look like, but that's okay. That's a start. Before we do anything else, let's put that back in. I'm believing of this cause. I believe these bounds are wrong, so I'm going to change this real quick. There we go. 0, then add a scatter. There you go. There you go. So this is a big part code in this. It's a debugging process. Snip out run, that should take a whole lot less. It's still running. There we go. That looks a lot better now I've changed these. This is one part I would do want to learn more about. Just get how these operate, how you know which side goes where. But I know one is very much incorrect and one is very much more accurate. So this is a rough plot of temperature over time. Of course, as time goes on, and you keep on going upwards. I prefer to have a more obvious scale for this, but you can see the gradual change from absolute, a vertical line, to something more appropriate, more horizontal as we approach infinity. So let me actually make this a little nicer. So minutes, and this would be divided by 60. I'm going back again. There you go, it's beautiful. I love it. It's got format text. It's not Plotly Dork. I know, commit grave sin. Oh no. But this is all plots. I've shown you how the thought process through this. Alright, here's parameters. So to X, I've shown you how we do the banded. So it's all one matrix. It's all horizontal. Because that's how solve banded processes it. So it wants a horizontal matrix, doesn't actually want the giant diagonal square one. But our diagonal variance here, and your notice the second one. Again, I have not taken any algebra, so more exact terms have to learn in another class. So this was a class. And how to get all the known values. So we know values, we can calculate easy equations before, and account with special boundary conditions by tacking on the extra properties, or sometimes just modifying them to make sense, because this one, since insulated, can't have any temperature differences because, well, then it's no longer insulated, it has heat flow. Integrate plot it, monitor 300s, clean the visual by 300s, 3, 4, or 5 minutes, and for plots, format string, or the numerical value you want to calculate, followed by minutes, and show all wonderful, wonderful magical plots at the end. So that concludes this. I'm gonna get upload this night. I'm gonna have it go rendered. It's no late now, but I'll stay up and I'll watch it. Also, thank you for this class. I know you're frustrated earlier, and I understand that. So I'm also kind of frustrated myself for being up this late and working on this, but definitely happened today, and I do appreciate it. I know it's it. And thank you.